Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Okay, grade 11s, welcome. We're gonna go through some revision of stoichiometry, or otherwise known as qualitative aspects of chemical change. Okay, very important section in the syllabus. Okay, very important section in the syllabus, and counts a large part of the chemistry paper, of course, in grade 11, as well as a bit in grade 12, as it is also expanded upon in grade 12. Okay, so very important section. So it's good that we're taking time to revise it. So we want to wake up our brain to the section and remind ourselves of course, good concepts. The first concept that we need to remind ourselves is of the mole itself. Now, we officially started learning the mole in grade 10. Also know this because I'm teaching it to my grade 10s currently. Okay, now we learned how to use basic mole calculations. We also learned how to use basic concentration calculations. Okay, but to remind ourselves of a few things. One, the mole is the quantity of matter containing the same number of elementary particles as there are carbon atoms in 12 grams of carbon 12. Okay, and which is the mole is basically the mole is the SI unit of quantity of matter. Okay, which is MOL. All right, so that's a definition we remember from last year. It's a definition found in any textbook, in notes maybe that your school has provided. You just go and learn the definition. I'm not going to have a look at it. I'm not going to rewrite it down here today. So in grade 11 now, what we actually did is that we took that same concept and applied it to reactions involving gases, as well as more complex stoichiometric calculations. Okay, so with the mole also involves something that's called Avogadro's number. Okay, now this is probably going back to basics as well. Okay, now Avogadro's number has a value in A, which is its symbol, is equal to about 6,02 or sometimes 6,023 times 10 to the power of 23. Okay, because 1 mole of a substance contains a fixed amount of particles. So this is the amount of particles that is found in 1 mole. Okay, again, take an example. 1 mole of water, H2O, will contain 6,02 times 10 to the power of 23 H2O molecules. All right, that's what it contains. Okay, now that's Avogadro's number. Now the formula, of course, with using Avogadro's number to calculate the mole, is that the mole is equal to Avogadro's number. Oh, sorry, the number of sorry, let me rephrase that. Calculate the mole. You use by is equal to the number of particles divided by Avogadro's number, which is obviously the amount of particles found in 1 mole, and this is the number of particles of any substance, and you'll get how many moles of that substance that you had. Okay, this is the formula for finding the mole using Avogadro's number. Okay, basic, pretty simple. Okay, let me just add a legend here quickly. Yes, 1 mole of substance here. So Na is Avogadro's number in the formula. Let me just add a legend here. Number, No, number of. N would be number of particles of a particular substance. Let me actually just, the whole point of saying No is number of. So No particles, number of particles. And then of course N is obviously the mole, which is measured in MOL. Okay, so that's the legend for the formula. Okay, the next part though is of the mole is of course calculating it using molar mass. Okay, which is the most common mole formula, which states under the formula the mole is equal to the mass of a substance divided by the molar mass of that substance. Okay, and so the mass of 1 mole of a substance is the relative formula mass of that substance expressed in grams. So M here, do a quick legend quickly. M here is mass of the substance, and it is measured, of course, in grams. The capital M here is molar mass of the substance found on the periodic table, and it is measured in grams per mole. Okay, and then of course where N is the mole, MOL is what it's obviously measured in. Okay, that seems quite basic enough. Okay, then there's of course another way to work it out with the molar volume of gases. Okay, so the third mole calculation formula that we learned, the volume of gases, of course. And now we obviously had a new formula, which I'll use another color for, is that N is equal to V divided by Vm. And if we draw the legend here quickly, of course, V would be the volume of the gas in decimeters cubed, and Vm would be what's known as molar volume. Okay, now molar volume is obviously calculated in decimeters cubed per mole. It's a -1, right? That's molar volume. Okay, and of course, molar volume will be measured, of course, at STP, standard temperature pressure. Okay, because 1 mole of gas occupies about 22,4 decimeters cubed. So usually this is also equal to about 22,4 decimeters cubed, unless otherwise stated in the question. Okay, so we've got 3 formulae for the mole. One with the particles. 1 mole contains 6,02 times 10 to the power of 23 particles, which is Avogadro's number. N is equal to capital N divided by capital Na. Then 1 mole also has a mass of a substance in grams. N is equal to, over here, M over big M. And then, of course, 1 mole of gas at standard temperature pressure has a volume of 22,4 decimeters cubed, and we've calculated using that formula there. N is equal to V divided by Vm. Okay, moving on now, we move on to something that's called concentration of solutions, or molar concentration of solutions. Okay, now in grade 10 we obviously learned how to calculate the molar concentration of very simple solutions. Okay, and by having a look, of course, at the formula, concentration is equal to the number of moles divided by the volume, of course, in decimeters cubed. Okay, now obviously now we'll be looking at a little bit more complex molar concentration calculations. Okay, for example, with this formula also we can also combine the formula for the mole. Okay, it's because if I write but N is equal to M divided by big M. Okay, and we see that N is present here, so we can form a new formula for concentration as well without doing too many things at once. C is equal to M divided by capital M times V. Something I just want to show quickly is how to convert the centimeters cubed to decimeters cubed. So if you want to go from centimeters cubed to decimeters cubed, okay, you need to divide by 1000. You divide by 1000 because 1 milliliter is equal to 1 centimeter cubed. Okay, and 1 liter is equal to 1 decimeters cubed. Okay, so if you want to go from centimeters cubed to decimeters cubed, you need to divide by 1000. Okay, so 500 milliliters is half a liter. Okay, your normal Coke bottle, 500 milliliters, half a liter. That's the conversion there. Alright, so on the screen there quickly, if you want to take an example 3 of a more complex calculation though, is if we have the calculation of mixing certain solutions under concentration, or the mole concentration. Okay, so they say the concentration of sodium carbonate solution, okay, shown in this diagram that we see here, okay, and this is from the textbook by J.M. Lucas, which is just called The Science Tutor, grade 11, physical science. And we can see that the solution of sodium carbonate is 0.2 moles per decimeter cube, so that is the concentration. And it is definitely beaker A, and it's 500 cubic centimeters, while the concentration of sodium chloride, which is beaker B, has 300 cubic centimeters, only with a solution of concentration of 0.4 mole per decimeter cubed. All right. Now they ask write equations showing the dissolution of each of the salts. Okay, the dissolution obviously showing the solutions ionizing. Okay, but question B is the most important one, as they say now that the two solutions are now mixed. What is the concentration of the sodium ions in the mixture? Okay, now how do we approach this? This is, of course, very complex. This is not easy. So if we can all just pay attention, it'd be lovely. Okay. Now they say, okay, that's all I need. Yeah, all I need. Okay. So when two solutions are mixed, the number of moles of sodium ions will obviously increase because you are throwing sodium ions into a beaker that already has sodium ions in it already, because both of these two solutions contain sodium. Okay. To determine the concentration of the ions though in the mixture, the total number of moles of sodium ions and total volume of the new solutions must be determined. Okay. So first of all, we've got to calculate what's the number of moles first. So for sodium Na2 CO3, sodium carbonate, of course, number of moles is equal to C times V, which is equal to 0.2, as we see over here, multiplied by 0.5. Okay, which is obviously 500 cubic centimeters, the same as 500 milliliters, so we just divide by 1,000. Okay, then that gives us answer of 0.1 mole. Okay, and now we obviously do of NaCl as well, same thing. N is equal to C times V, which is equal to 0.4 multiplied by 0.3, and that'll give us 0.12 mole. So we got the amount of moles of each of the substance. Okay, excuse me. So the first question comes into play here. They ask for the solution showing the dissolution of it. So if I do this over here quickly, Na2CO3 dissolutionizing, in other words, that's not even a real word, I don't even pay attention to it, that's just me being foolish, but it's obviously dissociating or breaking apart in water. Okay, that's going to become Na ions plus carbonate ions, CO3 2 minus. One moment please. Anyway, so we've got Na plus CO2, CO3 2 minus. Now all we've done here is we've just shown how sodium and the carbonate have disjoined. Okay, they have broken apart in the solution. Okay, they're both in aqueous solution. So in other words, we've shown the ionic equation for them. Okay, but obviously we need to balance the ionic equation to say that we've got two sodiums and here we only got one, so 2 must come in front of there to balance them out. Okay, then the next one, of course, is NaCl. So we've got NaCl was also dissociating or in water to become a solution, and we get, of course, Na plus Cl minus, all in aqueous solution. Okay, so now of the two substances, this is the amount of moles, right? So now in order to figure this out, okay, we've got to obviously say, well, this is the number of moles of Na2CO3. So then for this one over here, the number of moles of Na ions in the first one must be equal to, of course, because we see that it's got 2 over here, 2 times 0.1, which must equal 0.2 mole. Okay, and for the second one, the amount of moles in NaCl of the sodium ions Na plus, that is equal to just 0.12 because they're all in the same ratio. Okay, so now that I know the amount of moles of my sodiums, obviously if these two must come together, okay, for total moles, total N, okay, which is going to be 0.2 plus 0.12, that is going to give us 0.32 moles of sodium once it is now mixed together. Okay, and the total volume is going to be, of course, the 500 cubic centimeters mixed with the 0.3 decimeters cubed. So 0.5 plus 0.3, which is the 500 there, plus the 300, which gives us a total of 0.8 decimeters cubed. Okay, now if we want to bag that in a formula, okay, it's obviously going to equal concentration. Okay, I'm going to have to write this out in one line. Concentration is equal to the number of moles divided by the volume, which is equal to, of course, 0.32 divided by 0.8, and all of that new concentration of my sodium ions, which the question asks for, is going to be 0.4 mole per decimeters cubed. Okay, all sorted. No, don't need that. Alrighty, let's move on to what is known as the empirical formula. Okay, now empirical formula is the simplest whole number ratio of the molecular formula. Okay, it's the simplest ratio. Okay, the molecular formula, of course, is a multiple of the empirical formula. Okay, so let's take, for example, benzene. Benzene is obviously the chemical name, but the benzene molecular formula is given by C6H6. Okay, and then we've got the empirical formula, which, remember, if it's the simplest whole number ratio, okay, what is a ratio? How do you simplify a ratio? You obviously divide it by the smallest number. In this case rather, the smallest number on both sides is 6, so the empirical formula would just be C and H. Okay, so that's the empirical formula of benzene, which is the simplest whole number ratio. But in grade 11, we combine the simplest whole number ratio empirical formula with percentage composition, as well as or just basically percentage compositions. Okay, so they'll ask you to first calculate, of course, the empirical formula, and then you'll be asked or tasked to calculate the molecular formula there after that. Okay, so if, let's say, we have a compound that is made up of nitrogen is 30.4%, and we have another part of that compound, oxygen, is 69.6%, and then we need to determine the empirical formula. Okay, so first we've got to do of all of these is to now assume, because we haven't been told the amount of grams, we just now assume that all of this is going to, obviously this adds up to 100%, so this must add up to 100 grams. Okay, so in 100 grams of a compound, okay, if we take a sample, that might not be, but we know that in 100 grams of a sample, we know that there must be 30.4 grams of nitrogen and 69.6 grams of oxygen for it to make up 100 grams. Okay, now from this we can determine the mole ratio. Okay, so if we determine the mole ratio, nitrogen, so N of capital N, we have 30.4 divided by the molar mass of nitrogen, which is 4, which is equal to 2.2 mole, and then the amount of moles of oxygen, which would be 69.6 divided by 16, yes it is on my periodic table, that should equal to 4,4 mole. Alright, 4,4 mole. So now we can see if we put this in a ratio. I think I've got space now to the side here. It's super rad. Okay, if you take this in a ratio, the number ratio of n to O now is, of course, 2,2 to 4,4. So we're going to divide both sides, of course, by 2,2 to get into 1, of course, is to 1. So therefore, the empirical formula is equal to, or we could just say is, no, or NO, of course. Please don't say no in the exam. Okay, that will be the empirical formula. Okay, sorry, it's not 1:1. Sorry, I've made a very silly error. It's that's by itself, and that is 2. So it's NO2, which is, of course, is a substance called nitrogen dioxide. Okay, that's the empirical formula. Okay, but now a question or that can follow up from this. So now a follow-up question on this might be, let's say you've now calculated the empirical formula, and now they say there's a molecular formula of the same compound, and they give you the molecular formula, they give you the molecular formula molar mass. Now let's say the molecular formula molar mass is, let's say, 92 grams per mole. Okay, so it's 92 grams per mole is the molecular formula. So of the empirical formula, the molecular formula has 92 grams per mole. Now, how do you find the molecular formula from the empirical formula? Okay, one of the things that you do is you first find out what is the molar mass of my empirical formula. So my molar mass of my empirical formula is 14 plus 16 times 2, which is 14 plus 32. So 32 plus 14 must give me about 46 grams per mole. I took a bit longer because I did it in my head. Okay, and so this is the molecular formula's molar mass is 92, and the empirical formula's molar mass is 46. Now, if you do a quick calculation, I'm not the smartest person in the room, but 46 plus 46 must give me 92. So since the molecular's formula, or the molecular formula's molar mass is double the empirical formulas, okay, it's easy for me to find out my factor. Alright, my factor of this is obviously 2. My molecular mass is 2 times greater than my empirical formula. So therefore, my molecular formula is 2 times NO2, which should equal or should give me N2O4 as my molecular formula of this compound that contains 30.4% nitrogen and 69.6% oxygen. Okay, so that's the revision of stoichiometry done, and obviously we did complete it, but I'm only going to revise up until here. I don't want to go past most of the students' schools that they're busy with the section, that are currently busy with the section in school. I don't want to go further than the classes, so we'll stop here, and this will be our revision so far, although we have completed the section when we were supposed to do the section.